All right, good morning, everybody, and welcome to the cryptography course. We are happy that so many people signed up for this course, and it is my pleasure to introduce Anna Lysyanskaya. She is a professor of computer science at Brown University, and she's famous for her work in anonymous credentials, in particular, among other things. And we are very happy that she agreed to deliver this mini course for Ukrainian students all over the world. And the mini course is going to be on foundations of cryptography, minicrypt, cryptomania, and beyond that. So, Anna, the floor is yours.
Thank you. Thank you very much for the introduction. Дозвольте мені розповісти вам трохи про себе. Я виросла у Києві, звичайно, я можу говорити та розуміти українську мову. І, звісно, ви можете говорити зі мною українською. Але знаєте, як на іншій мові ти інша людина, по-українськи я ще маленька школярка. Англійською мовою я професор інформатики в університеті Брауна та криптограф. Я працюю в криптографії майже 30 років. Зараз гаряча тема, де моя робота важлива, це цифрова ідентичність Європейського Союзу. По суті, закони Європейського Союзу диктують, що вони використовують мою роботу. У п'ятницю я вам про це буду розповідати. У криптографії, як і в житті, вам потрібно знати, чого ви хочете, щоб отримати те, що ви хочете. Тому ми завжди починаємо з визначень. Потім ми намагаємося знайти алгоритми, які відповідають цим визначенням. Оскільки цей курс призначений для математиків, ми зосереджені на теоретичній базовій криптографії. Це означає, що ми більше піклуємося про визначення та перевірену безпеку, ніж про ефективність. Загалом легше отримати практичну та доведену безпечну схему, якщо почати з не дуже практичною, але доведено безпечної, ніж якщо почати з такої, яка ефективна на практиці, але абсолютно небезпечна. Окей, зараз ми починаємо. І в мене є слайди. And now I'm going to switch to English because, as I said, in Ukrainian, I'm still very young. But in English, I'm much more, much older. Okay. Questions. Okay, so the questions on chat. The homework problems are going to be at the end of, they're part of my slides. You will see what they are as I go through them. Okay, those are the only questions. So I'm going to start sharing my screen. Okay. And there we go. Okay. So today's lecture one is called minicrypt, and you will see what that means towards the end of the lecture. Oops. Okay. So let's talk about methodology. I said that just briefly just now. Let's do it kind of in English this time. So a recipe for a secure system seems to consist of 3 steps. Define how it should work for honest participants. Define what you mean by secure. Give an algorithm and prove that it satisfies the definition of security. And usually this proof requires some computational assumptions, such as p doesn't equal to np. So question is this obvious? Is that this is the methodology? And yes, it seems to be obvious, especially in hindsight. But the kind of historically, the earliest cryptography research prior to like back in the 70s didn't do this. And the first examples of this methodology, and this is the methodology we'll use in today's lecture, comes from Goldwasser and Micali's 1982 definition of security for encryption. And it's so important that they won the Turing Award for it in 2012. So the Turing Award is like the equivalent of the Nobel Prize in computer science. So the reason this methodology is really important is that you can't just say, oh, look, it works. You have to prove that something can be broken. So now the same thing in Ukrainian, just flashing it on the screen so that everybody's on the same page. This is just methodology. Okay, so now let's look at an example of where we use this methodology. So let's talk about secure encryption, because this is the first cryptographic application that comes to mind immediately. Okay, so what do we need to do in secure encryption if we want to define it? So first of all, we need to think, how does it work for honest participants? So it should consist of a key generation algorithm that selects an encryption or and decryption key K. That it also includes an encryption algorithm, encrypt, that takes a key K and for example, a bit or a message, and produces a ciphertext C. And then we also have a decryption algorithm that takes as input the key in the ciphertext and recovers the original message, for example, the bit B. Okay. And what the honest participants need to do is they need to be able to recover the message. So we want to say that it's correct if the functionality ensures that the output of decryption is the same as the input to encryption. Okay, so that was step 1 in our recipe. So now I have the same thing, but in Ukrainian. So визначте, що є безпечність. So we need to define what we mean by secure. Okay. So the intuition for security is that the encryption of a 0 needs to look the same as an encryption of a 1. And now we need to figure out, how do we define it formally? What does it actually mean? And for that, we need to first figure out who is our adversary. And that means we need to kind of define, formalize, what are the adversary's computational resources? What is he capable of doing? On input, what does he, and what kind of output does he want to produce? And how does he interact with other system participants? Okay. So let's define that. So let's define who is our adversary. And also, the intuition is the encryption of a 0 needs to look the same as the encryption of a 1. So we need to define what it means for it to look the same. All right, so who is our adversary? So the adversary is, we always think the worst case is the most evil adversary you can imagine. So in this picture, this is the most evil that I could find by doing a Google image search and enhancing it a little bit. Okay. So we're thinking of the worst case situation for who the adversary is in terms of computational resources. So, of course, the worst case would be the adversary has infinite computational resources, but that we'll see in a moment. That's not going to get us much. So let's think in a more standard way, standard computer science way, and complexity theory tells us that polynomial time is doable. So let's think of the adversary as the worst case algorithm that we can imagine that runs in reasonable time, which is polynomial time. So the honest participants, we want them to run, to be efficient, to have high speed. And we want the adversary's running time to be polynomial in that speed. So the first step is to kind of say, let's parameterize what that means. So the traditional approach is to say there's some security parameter, we're going to call it lambda, and the honest participants' running time needs to be fast in this lambda. So the key generation algorithm takes this lambda as input, and I wrote it in unary, so that means it takes lambda once as input. So the size of its input is lambda, and it's supposed to be as efficient as, well, we want it to be as efficient as possible in this lambda. Whereas the adversary's running time is going to be some polynomial, potentially quite big, of lambda. Okay, so that's what this lambda is. So it's kind of very important. We measure everybody's running time as a function of lambda, and everybody else, we want them to be efficient in lambda, and the adversary is the worst case. So the only restriction is that the adversary be polynomial time in lambda. Okay, good. So now we add this lambda, the security parameter, to everybody's inputs for the key generation and for encryption and for decryption. And also the adversary is going to take this lambda as input as well, because he's allowed to be polynomial in lambda. Okay, and this is not the only, so this is a standard complexity theoretic approach. It makes the theory very nice and clean. That's not the only approach. There's also concrete security. So there's other approaches that kind of use this one as inspiration, but they're a little bit more fine-grained, and we're not going to talk about it now because we have a lot of ground to cover as it is. Okay, so that's who the adversary is. He is a probabilistic polynomial time algorithm and polynomial time as a function of lambda. That's his computational resources. All right, so what about its inputs and outputs? Well, we want to think of the worst case. So we want to say this adversary knows everything there is to know about the system except for the key K. That's a very standard way of thinking about cryptography. It's called the Kirchhoff principle, if you've ever heard of it. Okay. And then the last question that we need to answer about this adversary is, how does he interact with the other participants of the system? And because we are thinking worst case, we need to imagine the adversary is kind of being in the middle of all the action. So he can observe everything about the system. The only thing he doesn't know is which specific message was encrypted. So the way that this is captured is we think of this, of the adversary's interaction with the system as an experiment. It's the way we think of experiments in probability theory. So what happens in this experiment? So the first thing that happens in the experiment is the key generation algorithm is run on input the security parameter. So the key generation algorithm has to be probabilistic, so it should be able to flip some coins. And it creates a key, which it gives to both the encryption algorithm and the decryption algorithm. That's the first thing that is run. Then the adversary gets to interact with the encryption and decryption algorithms as black boxes. So he cannot see inside of them. He cannot know the key, but he can interact with them. And this kind of corresponds to the adversary is trying to attack the honest participants who are using this encryption scheme. So that means that he is allowed to send messages to them and to see their responses. He can send them messages to encrypt and see how they encrypted them. And he can also send them ciphertext and see how they decrypted them. So the way that we're going to capture it is by saying this is part of the security experiment in which the adversary can say, can issue encryption queries. So here he is. Here's his first encryption query to the encryption algorithm. Says, I want to see an encryption of M1, and he gets to. So the encryption algorithm runs on, plugs M1 into its input and produces a ciphertext and responds to the adversary and says, here's the ciphertext. And then the adversary also gets to run decryption queries. So he says, here's my ciphertext C1 tilde, and here, and C1 tilde gets plugged into the decryption algorithm, and he gets the responses. So after he's done all of that, a bunch of times, so as many times as he wants, as long as it's polynomial, now the adversary might say, all right, now I've learned enough about the system that I am ready for a challenge, for an encryption challenge. So he says, so this is the next phase, the query phase. That was the query phase. And then the next phase is the challenge phase. He says, now I'm ready, encrypt one of these two messages, either M0 or M1. And the only limitation here is that because the adversary will get to see the ciphertext, and the ciphertext, the length of the ciphertext is kind of an upper bound on the length of the message, we insist that in this phase, these two challenge messages be the same length, because otherwise you might be able to distinguish which one of them it was just based on the length. So the adversary says, here are two messages. I would like you to challenge me on one of those. The encryption algorithm picks one of the two messages at random. So flips a coin, picks the bit B, and plugs in that message into the encryption algorithm, produces a ciphertext, and says, okay, adversary, good luck. Try to figure out which message I encrypted based on the ciphertext C. And after that, the adversary still, so this was the challenge phase. After the challenge phase, the adversary doesn't just disappear. He then proceeds to issue more queries. So he can continue querying the encryption algorithm and receiving more ciphertexts, checking what ciphertext look like. And he can also continue querying the decryption decryption algorithms, with the only restriction that, so this is our restriction, he cannot just take the ciphertext that was his challenge and ask the decryption algorithm to decrypt it. That's not allowed, because then it's just too easy. Then he would be, of course, then he would know which message it was. But other than that, he can issue any decryption query. Okay, so that's how the adversary interacts with the system. And then in the end, he produces some output. And this is kind of the summary of what we just saw. So we're thinking worst case. So in the worst case, the adversary can observe the whole system and control most of what's going on. So in the worst case scenario, once the key is chosen using keygen, the adversary can run in polynomial time in the security parameter lambda and can query encryption and decryption to as much as he wants. This should be a little dot, okay. And then he can pick any pair of messages, M0 and 1, as long as they're of the same length. He gets a challenge C, which is the encryption of one of them picked at random. Then he can query, encrypt, and decrypt some more, as long as he doesn't ask for the decryption of this challenge ciphertext. And finally, he produces an output. So that's how he interacts with the system. And then finally, what does it mean that the system is secure? So this is the punchline. What it means is that whatever this output is, it is the same, which we haven't defined what that means yet, whether or not M0 was picked or M1 was picked. What does it mean that it's the same? So one interpretation is that it's literally the same. That doesn't work, because what if the adversary just takes the ciphertext and just outputs that? Then it's going to be different, because different message results in different ciphertexts. So that's too much to ask. So instead, what we're asking for is we're going to measure the probability of the event of some event. For example, a convenient event whose probability we can measure is what's the probability that the adversary outputs 0 after all of this perturbation, after this whole interaction. So we can measure the probability he outputs 0 when we chose message 0. So that will be our P0. And we can also measure the probability when we had chosen message 1. So we can also measure the probability that the adversary outputs 0 when the original message was, when the encrypted message was M1. And our goal is to say, no matter which message was encrypted, the probability of this event is the same. So we would like to be able to require that this P0 equal this P1. Unfortunately, we can't. We cannot insist that they be exactly equal. That's too much to ask, because there's a small probability that somehow the adversary guesses the key K. It's hopefully not a very big probability, because we're hoping that the key K is going to be lambda bits long. So if you just guess at random, you're going to be correct with probability only 2 to the minus lambda. So that's very small, but it's not 0. So we cannot require that these P0 strictly equal P1. So the best we can do is require that they be close. Okay, so that if we want it to be close, we need to define what that means. So for that, we need to define the notion of a negligible function. So instead of, again, let me just recap. Instead of requiring that they be exactly equal, we require that their difference is very small. Very small, called negligible. So I translated it negligible as neznaczna funkcja. Duża malenka. So the intuition for what this negligible, what the notion of a negligible function is supposed to correspond to, is that, let's say you conduct a series of experiments, and there's some event whose probability is negligible. So if it's negligible, that means that if you only conduct a polynomial number of experiments, you're pretty much guaranteed to never see the event happen. That's the intuition. And the more formal definition is this nu of lambda is negligible if it is asymptotically smaller than any inverse polynomial. So if nu of lambda is less than lambda to minus c for any constant c for sufficiently large lambda. I'll pause here just to catch my breath. So this is a new and counterintuitive concept. Here's some examples to help us think about negligible functions. So for example, 2 to the minus lambda is negligible. And even something much smaller like lambda to the minus log lambda is also negligible. So the point is that if you only conduct a polynomial number of experiments, in each experiment the event's probability is negligible, then the event's just not going to happen. It's very, very unlikely. That's the intuition. Okay.
Excuse me.
Yeah.
May I ask a question?
Yes, of course. Go ahead.
I didn't quite get what these events are. A output 0 when B is equal to 0, and A output 0 when B is equal to 1. Could you please clarify?
Yes. So if we look on the previous slide, okay. Previous many slides, sorry about that. Let's do this slide. Okay, here we go. So our adversary is interacting with the system. Lots of things are happening, right? So we've generated the key. We have allowed the adversary to see ciphertext of messages of his choice. We have allowed him to decrypt ciphertext of his choice as long as they're not a challenge ciphertext. And we have issued to the adversary a challenge. What's our challenge? The challenge is the ciphertext C, which is an encryption. Oh, this should be M sub B. Sorry about that. It's a slight mistake in the slide. Let me fix it before you get too confused. This is M sub B. M sub B. All right, here we go. So the challenge ciphertext is an encryption of a mystery message. Either it's M0 or it's M1. Okay, so we have two different experiments. In one experiment, M0 is encrypted. In the other experiment, M1 is encrypted. Okay, so in these two experiments, everything else is the same. So we can measure the probability now to go here again. We can measure the probability that A outputs 0 in the experiment when B is 0. And it's some number, right? It's some number between 0 and 1. Whatever it is, it depends on how the adversary works and when he outputs 0. We can also measure the probability that he outputs 0 when the challenge ciphertext is an encryption of M1. So that will be the probability P1. Okay. So does that
B is an index of a message encrypted, not the message itself.
Correct. Yes, that's right. That's exactly. So let's go back to this summary here. As you can see in the two, let's just say worst case scenario, parameterized by bit B. Okay. So we have experiment 0 and experiment 1, depending on whether bit is B is 0 or 1. And everything is the same in the two experiments, except for which message gets encrypted. How does that sound? Does that resolve the confusion, or should I pause and answer some more?
Yes, and what does output of an adversary mean? What does 0 mean when A answers 0?
That's a very good question. So the 0 doesn't necessarily mean anything. It's a placeholder for some event. Let's say whatever it is that's a bad event. Let's say that, for example, the adversary's goal is to find out something. And he runs some algorithm, and then he's at the end of the algorithm says, did I learn whatever it is I was trying to learn? Am I happy? Like, did I succeed? So the 0 is meant to capture that, because if there's some event of interest, depending on what the adversary is trying to do, it might be a different event. But you can always reduce it to, if the adversary is happy, he outputs 0, right? For any adversary, without loss of generality, you can transform him into one that's gonna, if he's happy, he outputs 0. So that's what that's meant to convey. So let's say that this ciphertext gave the adversary enough information to act on it and be successful. That's what the 0 is meant to capture. Is that, like, keep asking me questions, because this is a very, very important point. So
can I try to reformulate what you just explained, maybe
sure,
a little bit more mathematically, and
go
you
ahead.
tell me if I'm right or wrong. I could be wrong.
Sounds great.
Again, about this 0 and 1 thing.
Uh-huh.
So I imagine that the adversary knows how encryption works.
Yep.
Knows the algorithm, how encryption works, knows the algorithm, how decryption works.
Yep.
The only thing the adversary does not know is the key.
And the bit
right?
B.
And the bit and the messages which are being fed into the machine, right? So, and then you
He
say that
knows. He does know the messages, that because he feeds them himself. He knows everything except the bit B.
yeah, if he feeds him, yeah.
Yep.
I think I understand that.
Yep.
And now you say that so the only thing the adversary does not know is the key, and you give the adversary kind of the easy task. The hard task of adversary would be to have a message that the adversary does not know and then actually decipher, right? That's ultimate goal. But you give the adversary an easier task. You say, okay, here are two messages that you know.
That you picked yourself. Not only do you know them, you picked them yourself.
Yeah.
Yep.
You pick them yourself, and based on all your knowledge, you say adversary comes out with some algorithm, and the question is, can the adversary distinguish between M0 and M1 based on the encrypted output? And now let me say a mathematical thing. Maybe I'm wrong about it. So suppose adversary design a probabilistic algorithm, which means there is some, let's say, some discrete probability, like, I don't know, 2 to the n outcomes.
Okay.
And it's a probabilistic algorithm, and so there is a probabilistic input, and based on this probabilistic input, the adversary does something, and then the adversary says, okay, this message is M0, or okay, this message is M1. And I think your definition basically says that in this way, there is a kind of a well-defined probability of M0, and your definition simply says that probability is less than exponential from 1/2, right?
So what you're describing actually would be an equivalent definition, but it's not the definition I just gave. The definition I just gave, you look at all of the possible outputs. So let's say that your adversary's output is not 0 or 1, that your adversary's output is much more interesting, much more complicated. But there is a finite, as a function of lambda, set of outputs. And you can just, and so at an event, we can define an event that the adversary outputs something interesting. So that means any set of outputs can be like, there's some set of outputs that's in the event and some that are not in the event. So then we can define another adversary, like A prime, that is just for this event. If the outputs are in that event, then this A prime outputs 0, otherwise outputs 1. So now that event means the adversary is happy, whatever that means. We don't know what that means. So now whenever A is happy, A prime outputs 0. So we're measuring, is our adversary going to be happy when we give him an encryption of 0? Is he going to be happy when we give him an encryption of 1? Does his happiness change? So that's what we're measuring. So it's indistinguishable because indistinguishability means that the adversary's output isn't really affected by whether we encrypted a 0 or we encrypted a 1. So whatever it is that we encrypted, the adversary's behavior is the same.
When you say encrypted 0, encrypted 1, you actually mean M0 and M1.
Yeah, that's what I mean. Sorry. Yes,
Okay.
I mean M0 and M1.
Mhm.
Okay. Does that... And your intuition is actually very good because it's a kind of an equivalent notion. We can also say, here is an encryption of a mystery message. Try to guess which message it was. And security means that you can guess with probability only negligibly different from 1/2. So it turns out that these two definitions are equivalent. I chose to give this definition as opposed to the other definition, but it's actually I'm not going to assign that as a homework exercise because it's a little hairy. So people get, but it's actually a very nice homework problem for when I have more time to teach this stuff. Okay, so it sounds like we got...
Can I ask a question too?
Yes, go ahead.
As I know, there is a notion of, I don't know term in English, абсолютна криптостійкість. There is a functional of informational
Perfect
entropy.
security.
And
Yes.
we consider that some ciphering algorithms are absolutely crypto something.
Yeah. So
And
no.
when
So
if and only if ciphertext does not give any information about plain text in the terms of informational entropy.
Yes,
so,
that's correct.
And there is some, and I know an example, Vernon cipher. But in that case, how does the adversary can distinguish between inputs they themselves chosen to cipher?
So Yehor, I have to tell you, none of those ciphers satisfy this definition. This definition is a little different. And I hope that when, by the end of the lecture, you will know what the answer to your question is.
Okay, thank you.
Okay. Okay, good. So let's keep going. We have a lot of ground to cover. That's why I'm a little impatient. Okay. So now this is a very, very important definition of this indistinguishability. And for this definition, Goldwasser and Micali won this Turing Award. So here's a picture of them once they won the Turing Award. So this is kind of a key to defining security for most cryptographic schemes. This is a super important notion, this indistinguishability, and it's a little tricky to wrap your mind around. Okay, so now that we know, now that we've done that, let's look at our recipe for secure encryption. So remember, we have a recipe for getting a secure cryptographic scheme, for secure any secure scheme, and in particular, we're using secure encryption as an example. Is step 1, we need to define how the system should work for honest participants. We're done with that. The honest participants encrypt and decrypt. We have defined what you mean by secure. So now we're ready to give an algorithm and prove that it satisfies our definition of security. So here is actually where I'm going to address yours question. Usually this proof requires some computational assumptions such as P doesn't equal to NP. So let's get to that. Why does it require computational assumptions? Okay. So, and this is actually going to be your first homework problem. So I'm not going to spend a whole lot of time on this. But suppose that P equals NP. Then I claim that if P equals NP, then after some number of queries, the adversary will find the key K. And, but just so that I am not setting you up for failure, can you please use your Zoom interface and give me a thumbs up if you know what P and NP are? Okay, I see some thumbs up. Not everybody's giving me a thumbs up. Okay, so P versus NP is kind of the most famous open problem in theoretical computer science. And it concerns itself with whether polynomial time algorithms exist for problems such as circuit satisfiability. So this is kind of important, and I'm not going to address it in this lecture, but since some of you need a refresher on this, it would be helpful if before you do the homework, you look up what that means, what that notion means, because that's kind of important. Okay, now I need to figure out how to make the Zoom window disappear so it doesn't block my slides. Okay, great. Here we go. All right, so it turns out that in order to satisfy this definition, in order for there to exist an encryption scheme that satisfies the definition I just gave, it has to be the case that P doesn't equal to NP. So because we don't know, it's an open problem whether or not P equals NP. Most computer scientists believe that they're not equal, only because that's our intuition, not for any other reason. We might be completely shocked tomorrow if somebody proves that they are equal. But, you know, hopefully we're correct. So we have to make assumptions. So it turns out that actually we need to make a stronger assumption than P versus NP. Namely, we need the necessary and luckily sufficient assumption for encryption, the way I defined it, is the existence of one-way functions. And I haven't defined them yet, so that's coming up. But let me just reiterate it. Secure encryption, as I just defined it, exists if and only if one-way functions exist. And my best translation of the words one-way function into Ukrainian is одностороння функция. So I hope that sounds correct. Feel free to suggest other translations. Okay, so what is a one-way function? So that's another definition we need to get through. Okay, so let's say that we have a function f that takes k bits of input and produces some n of k bits as output. N can be any polynomial. And let's say that it's sufficiently computable, polynomial time computable, and it's well-defined for every k. So for an adversary A and an integer k, let's consider an experiment where we pick x uniformly at random. Then we run the adversary on f of x, and the adversary outputs some x prime. And the event whose probability we want to measure is the event E sub ak, in which the adversary's x prime happens to be the preimage of f of x. So f of x prime is equal to f of x. So f is a one-way function if that event's probability is negligible, if it's hard for the adversary to do that. So I wrote that in English and I wrote that in Ukrainian. So I hope it's clear what the definition is. I actually have nice, so this is kind of pictorially. It's easy to go from x to f of x, but it's hard to go back. So I have a more compact notation for describing these experiments. So in some later slides, this is the notation I'm going to use. Inside this probability expression, first, there's something that just describes the experiment. It's not part of the probability space. It's just a description of the experiment. And then it's the event whose probability we're measuring. So f is a one-way function if for any probabilistic polynomial time adversary A, so I abbreviate this probabilistic polynomial time using this PPT. Once you have chosen a random x, so this is how I denote the part that x is chosen uniformly at random from the space of k-bit strings, then you have fed f of x to the adversary, and the adversary produced x prime. The event in which f of x prime is equal to f of x is negligible. Okay, so that's a one-way function. Easy to compute in the forward direction, hard to find the preimage. Okay, and this is the same thing said again. Okay, so now remember our theorem is secure encryption exists if and only if one-way functions exist. So there are two directions to that proof. It's necessary to assume one-way functions and it's sufficient. So the necessary direction is a little bit easier, and that's a homework exercise. So the homework exercise is to show that that if secure encryption exists, Then we have this encryption algorithm. And if you think of the encryption algorithm as a one-way function of the key K, the message M, and a sufficient number of random bits R. Sorry, if you think of encrypt as a function, as a deterministic function that takes as input K, M, and R, then it's a one-way function. Okay, and that's a homework exercise. Okay. So that's the easy direction, it turns out. I mean, it's still not a trivial exercise, but I'm going to leave it to you guys to figure it out why it's necessary. So now, why is it sufficient? Okay, so here is about, well, many years, several decades worth of cryptographic research in one slide. So the roadmap to constructing secure encryption from one-way function consists of 4 easy steps, not so easy steps. The first step is to construct a pseudo-random generator from a one-way function. The second step is to construct a pseudo-random function from a pseudo-random generator. The third step is we construct something called the block cipher from a pseudo-random function. And then the last step is we construct symmetric encryption from a block cipher. There are easier ways, but these are kind of the 4 standard steps that it's a good idea to know. So I'm going to tell you about them in the next 15 minutes, but quickly. Okay, so that's our plan. And little warning, that's actually, if you're interested in how encryption actually works, so right now we're speaking on Zoom. Zoom actually uses encryption. So somebody who's eavesdropping on the network right now will not be able to figure out what I'm saying. The way that Zoom uses it, that encryption scheme that Zoom uses was not constructed using that recipe I just showed. It kind of short-circuited some of the steps. So in real life, the way that it works is the cryptography research community kind of came up with a block cipher first, like directly. They didn't construct a block cipher from a one-way function. They just came up with a construction that they analyzed for a very long time and decided that it was good enough. So in the US, the National Institute of Standards had a competition for block cipher design. So the reason that I still want to tell you about all the steps is because they're very important to kind of understand the cryptographic methodology, and they're very cool in theory. Okay, and NIST, but in case you're having any doubts about the fact that AES was kind of designed not from a one-way function, but it's just it's just designed from scratch. Don't worry, this competition took many years to complete. It involved hundreds of researchers looking at various candidates that were proposed and trying to break them. AES was adopted more than 20 years ago, and it still stands. So it's fine. And I actually just visited the National Institute of Standards 2 weeks ago, and I visited it because the National Academy of Sciences is reviewing the work of the National Institute of Standards. So we're writing a report. So NIST is an amazing organization, and this is the way that Zoom is doing encryption using AES is fine. All right, now back to our theoretical programming. So this is our plan. So if the first step in our plan is to construct a pseudo-random generator. Okay, so first of all, what's the definition of a pseudo-random generator? Okay, we already know how to say something is indistinguishable, so we can use that notion of indistinguishability to define what it means for something to look random. All right, so what does it mean? So we can again define we can measure 2 probabilities. The probability that an adversary outputs 0 in the event that he's given the output of some algorithm, and in the event that he's given a truly random string. Okay, so this is kind of our roadmap. But first, okay, so what's an idea of a pseudo-random generator? It's an algorithm that takes as input a short string, k-bit string, and outputs a longer string, for example, a string of length 2k, and that longer string looks as if it was output, as if it was chosen uniformly at random. And to define again, so what does it mean? It means that if you take any probabilistic polynomial time adversary A, and you measure the probability that A outputs 0 in the event that he was given the output of G, and you also measure the probability that he outputs 0 in the event that he was given a string R that's chosen uniformly at random, those two probabilities are going to differ by only a negligible amount. Okay, so we're using the same approach to defining a pseudo-random generator as we use for defining secure encryption. Okay, so
Can I ask a question?
Boris, yep, there's a question.
Yeah, is this algorithm deterministic that encrypts a string of length k?
Oh, you mean this is not an encryption algorithm. This is a pseudo-random generator algorithm. And yes, it is deterministic. It takes as input a short S, and it outputs a longer R. And there's another comment on the chat. Oh, the comment on the chat is a question of whether hash function is an example of a one-way function. Yes, but we haven't actually defined a hash function yet. Actually, also not any hash functions. A cryptographic hash function is an example of a one-way function. Okay. So here's a theorem. If one-way functions exist, then pseudo-random generators exist. This is a theorem from, actually, it's kind of a classic in cryptography, and it's already quite an old theorem. It's more than 30 years old. It was proven by Hosted, Impagliazzo, Levin, and Luby. And just to give you a little bit of a flavor for how it works, it's kind of a beast of a theorem that takes several weeks to cover properly. So this is going to be a 2-minute version of a theorem that takes several weeks to cover. So let's try to construct the pseudo-random generator from a one-way function. So this is the first attempt. It's completely wrong. The first attempt is let's draw a random x and output x concatenated with f of x, where f is a one-way function. This totally doesn't work. This was just a little warm-up. The reason it doesn't work is that you can easily distinguish whether R was drawn from uniformly at random or is the output of this algorithm by checking whether the second half of R, y, is equal to f of x. So totally broken. Okay, so here's another attempt. So this attempt is kind of getting there. So the other attempt is, let's define a Boolean function such that if you're given f of x, you cannot determine b of x better than at random guessing. So in other words, let's measure the probability that an adversary correctly outputs b of x on input f of x. Let's call this probability PBA. We want this probability PBA to be negligibly close to 1/2. Okay, and this function is this function b is also known as a hardcore bit of a one-way function, and also sometimes it's called the Goldreich-Levin bit. And in case you are, following the life stories of famous people, famous computer scientists from Ukraine, so this is the same Levin as in the Cook-Levin theorem, and he is from Dnipro. He lives in Boston now, so if if you're interested in me name dropping people, he's one of the people that I occasionally run into. Okay, so our second algorithm uses this bit b, so it outputs R. R is f of x concatenated with b of x. So this doesn't quite work because, first of all, the output is too small. It's only k plus 1 bits, and we wanted 2k bits, so we need to extend it 2 more bits. Second of all, f of x doesn't necessarily look random, right? X was drawn uniformly at random, but once you apply f to it, it might not look random at all. And the third question is, what is this B? Does it even exist? So for that, the answer is yes, because we have a Goldreich-Levin theorem, and we have a book for this class, which I'll tell you in a moment, that covers it very well. Not that you'll be able to read it in one day, but it's there. Okay, so now algorithm 3, let's make our life a little bit easier. Let's say that f is a one-way permutation, not any function, but a permutation. Permutation means that that the output of f of x has a unique inverse, and any string, any k-bit string, is going to have an inverse. Okay, so if x is uniformly random and f is a permutation, then f of x is also uniformly random. And let b be a hardcore bit of this f. Then if we draw a random x and output r equals f of x concatenated with b of x, now we got ourselves a pseudorandom generator that only outputs k strings of length k plus 1. So it only extends the length of its input by 1 bit, but at least now it actually is indistinguishable from random. Okay, so now the construction is called the Blum-Micali pseudorandom generator. The construction is, this construction just kind of iterates the other construction and outputs 2 k bits. So there it is in all its glory. But the point is, you keep applying the function f and you keep outputting the bit b. And the proof that this construction actually works is also gives a very nice technique for proving security in cryptography called the hybrid argument, where you generate the string. It's like you generate it algorithmically, and then at some point you hybridize truly random bits. And the proof shows that like every step of the way is indistinguishable from the previous step. Sorry, I have to kind of do it very quickly because we don't have a lot of time. But anyway, this is sort of the roadmap for how we construct a pseudorandom generator from a one-way permutation. Okay, but it only works, this is fundamental, this only works if f is a permutation. And on the homework and also the problem solving session tomorrow, you will see why. And the reason for that is that if you apply f once, it's a one-way function. But f of x might not be a one-way function at all. In fact, it might be a constant function. So it degrades, and then you won't be able to iterate this construction. Okay. So if we want to get a pseudorandom generator from any one-way function, and in particular one that's not a is not a permutation, then the construction is a little bit different, and it involves an additional function g that kind of randomly moves the output of f. So this is very, very high level, but the point is you start with your random x, then you output its hardcore bit, then you move it using the function g, you move it to somewhere else using the function g and some public randomness, public parameter ri, and then you apply the function to that. And this is very high level. But so I'm just going to stop at that because there's still a lot of other steps to get through. Okay, so then from a pseudorandom function, from a pseudorandom generator, so the next step in our roadmap is we construct a pseudorandom function. So what's a pseudorandom function? It's a function that, first of all, it's efficiently computable. And secondly, it looks, when you interact with it, when you just feed it inputs and observe outputs, it looks as if it's a truly random function. So in other words, the pseudorandom function it has 2 inputs. One input is a seed. The other input is the input x, and it produces a k-bit string. And it is pseudorandom if no adversary can distinguish between the 2 experiments that I'm going to show you in a moment. So in both experiments, the adversary can query something as a black box. In experiment 1, he is querying the function f. In experiment 2, he is querying a truly random function. And in this, with he's querying f, of course, there needs to be a seed for the f. So the seed is picked uniformly at random. And now here's how these black boxes interact with the adversary. So in both experiments, the adversary has this oracle that he can interact with. So on the left-hand side, the oracle has the seed S hardwired in it, and it's deterministic from once S is fixed. And in the other experiment, this is just a truly random function that for each distinct query is going to produce a truly random answer. So the adversary says, here's my query, and gets a response. And then he can query it as much as he wants. And then in the end, and then in the other experiment, the same thing. He can query it as much as he wants. And then in both experiments, in the end of the day, the adversary produces some output. So a function is, f is a pseudo-random function. Sorry, I was going to rewind to the way I defined it. Oops. So f is a pseudo-random function if the probability that the adversary outputs 0 in his experiment with f, in the experiment when he's querying the function f, is negligibly close to the probability that he outputs a 0 in the experiment where he's interacting with a truly random function. Okay, so that's our, now I have to rewind, fast forward this again. Okay. Okay, so that's what a pseudo-random function is. And it turns out that you can construct it from a pseudo-random generator. And the way you construct it, this might be too much to read, so let's look at the picture. The way you construct it is when you get you have a seed S, and let's say that you have a query. Let's say in this picture, let's pretend that your X, your query is always 3 bits long. So if the first bit of the query is 0, then you apply the pseudo-random generator to your S, and you get a string of length 2k. Let's call it S0 and S1, and you just take S0. Then for the next bit, let's say it's 1, you again apply the pseudo-random generator to S0, and you get a string of length 2k. You split it into 2 halves, S00, S01. And because the next bit of your input is 1, you take this direction. So this is the picture, and now this is the actual code. Is if you have a seed S and a query X, you define the seed S empty string that corresponds to empty string to be equal to your original seed. And then you, based on the next bit of your X, you compute the seed that sits at the I-bit prefix corresponding to X using the pseudo-random generator. All right, so you kind of go left or right depending on what's the bit. Okay, and the proof of security also uses a hybrid argument that's very cool, but no time for it. Okay, so now we know how to construct a pseudo-random function from a pseudo-random generator. And it turns out that from a pseudo-random function, we can construct something called a block cipher. Because a block cipher is just like a pseudo-random function. So what's a block cipher? It's just like a pseudo-random function, only it's a permutation, and you can query it in both directions. And we can see how you construct one from a pseudo-random function in the book. Okay, so now we've constructed a pseudo-random. Now we've constructed a block cipher, and the block cipher is what we use for secure symmetric encryption. So here's an example of how you can use it. So let's say that here's your message. You split it into fixed size blocks of length k. And then let's say that E denotes the block cipher evaluated in the forward direction, and D denotes the block cipher evaluated in the reverse direction. And they both have this key K as input. So the CBC mode is actually, it was used very widely, but there's some issues, and it does not satisfy our definition of security. So it's one of your homework problems to see why this way of using a block cipher doesn't actually satisfy the definition of security I presented. But it's close. Fixing it is not that difficult, so you can fix it. You can figure out how to fix it. So the way it works is you start with let's start with a random C0. So let's pretend that we have like a random string to start the ciphertext with. You XOR it with the 0th block of your message. You can also think of a 0th block of your message as a random block if you don't want this one. You XOR them, you evaluate, then you feed them to your block cipher, and you get this block of the ciphertext, which you take and you XOR with the message, and you feed that again. So this results in your ciphertext. So in this example, there are only 3 blocks of the message. And then to decrypt, you kind of do that in reverse by using the inverse of the block cipher. Okay, so that's how you could, this is close. This is with a slight fix. This is how you can use a block cipher to encrypt. And this is how we're using it right now on Zoom. Okay, so now the next question is, can you get public key encryption from one-way functions? And this is where I finally explained the name of today's lecture, which is minicrypt. So because there's so many open problems in this space, we don't even know if P equals NP, there are many versions of what the world might look like. So Voltaire said that, well, it's not Voltaire, but Voltaire wrote this book called Candide, in which this is very famous line. There's a character that says, well, we live in the best of all possible worlds. So those are like Voltaire's worlds. So in cryptography, we have Impagliazzo's world. So this is Russell Impagliazzo. Doesn't really look like Voltaire. He has hair in different places than Voltaire did. Anyway, so Russell Impagliazzo came up with these 5 possibilities of what the world could be like. In one version of the world, maybe P equals NP. Then there's no cryptography at all. Then there's another kind of equivalent to it. But the good news about P equals NP is that now you can solve all kinds of cool optimization problems. So it's not so bad. And then there's heuristica, that's where P doesn't equal to NP, but you can still solve all the problems. It's almost the same. Then there's this terrible world in which P does not equal to NP, but one-way functions don't exist. So, you know, you can't solve optimization problems, and also you cannot do cryptography. Then there's the world in which one-way functions exist, but public key encryption does not. And in fact, he has a paper that shows that this version is plausible. Like it could be that one-way functions exist, but public key encryption does not. And then there's another world called cryptomania, in which you can have public key encryption and more. So next lecture, we're going to talk about cryptomania. So today's lecture was just minicrypt. And then you might be wondering, what about digital signatures? Actually, you can construct digital signatures from one-way functions. So one-way functions also happen to be necessary and sufficient for digital signature schemes.